Welcome to Lesson 11 of Puzzles to Exercise the Mind. What positive whole numbers can be written as the sum of consecutive positive integers? I have a few examples here. So, for example, 15 can be written as 4 plus 5 plus 6, and it can actually be written in more than one way. It can be written from the sum from 1 to 5, and also just 7 or 8. So, three ways of writing 15 is the sum of consecutive integers. 17 we can write as 8 and 9. 21 can be written as 6 plus 7 plus 8. 89 can be written as 44 plus 45. So you may want to give this a try and see which integers can be written as the sum of consecutive whole numbers and which cannot. And just as a hint, I guess, to give you, try doing it for the numbers from 3 to 16 and see if there aren't some numbers in that set which you cannot write as the sum of consecutive integers. These numbers, the ones that can be written as the sum of consecutive integers, are known as polite numbers, and the ones that cannot be known as impolite numbers. It's kind of I guess, a funny name they were given. So there's an article in Wikipedia on this, and then there's also a section in a book by Paul Halmos, Problems for Mathematics, Young and Old. It's problem 3G, and if you don't want to buy the book, you can borrow it from the Internet Archive. I gave the link here, and I'll also put these links in the information to this video, so you don't need to copy these down. You can just click on them from the information underneath of this video. So we're going to break the problem into cases. The first case is easy. If n is odd, then an odd number is just one different from an even number, which means we can write it in this form, 2k plus 1. And 2k plus 1 can be written as k plus 1, but these are consecutive integers. So, for example, 87 can be written as 2 times 43 plus 1, and then our k would be 43. And using this formula here, we get 43 plus 44, and that equals 87. So in the case that n is odd, you can always write it as the sum of only two consecutive integers, actually. And you may want to give it a try using this formula. Try 111, for example, and see if you can write it as the sum of just two consecutive integers. That doesn't mean that in some cases you can't write it as the sum of 3 or 4 or some larger number of consecutive integers, but you can always write an odd number at least in terms of two consecutive integers. For the case that n is even, there's two subcases. Either n is of the form 4k, in other words, a multiple of 4, and I've just shown you some of the examples, 4, 8, 12, 16, so on. Or it's of the form 4k plus 2, which would be 2, 6, 10, 14, 18. So these are the two possible cases. This case is easier to deal with, and we'll deal with it on this slide. If you're in the form 4k plus 2, you can write that as this sum here. And notice that you have k plus k plus k plus k. You have 4k. Then the minus 1 and the plus 1 cancel, and you just get 2. So this equals this, but these are 4 consecutive integers. So, for example, 50 equals 4 times 12 plus 2. So k is 12 in this case, and you just plug that into here, and you get 11 plus 12 plus 13 plus 14. You can see that's 50. This is 11 and 12 is 23. 13 and 14 is 27, and when you add those, you get 50. The case where n is of the form 4k is harder. We're going to talk about that on the next slide. But I just want to point out where you're a power of 2, which would fall into this category here, it's not possible to write the number as a sum of consecutive integers. And those are what I mentioned as the impolite numbers. We need an intermediate result before we handle the case of an integer being a multiple of 4. And that's what I want to look at here. So every even number can be written in the form 2 to the k times m, where k is a non-negative integer and m is an odd integer. This follows from the fundamental theorem of arithmetic, which states every integer has a unique factorization. So just in terms of an intuitive proof, if you know that when you have an even number, it's divisible by 2, and you can just factor that out. And if what's left is still an even number, you can factor that out again, and you can keep factoring it out. And what you end up with is either something that's a power of 2, where your m is just 1, or you have a power of 2 times some odd integer other than 1, 3, 5, 7, etc. So this is the crux of the problem of why you can't write a power of 2 as a consecutive sum of integers. You'll see that in the next slide. It all depends on being able to factor your even integer as a product of an even number and an odd number. And you can't do that with the powers of 2 other than just this trivial case where you have a 1 here. So we'll see that in the next slide, but just keep this result in mind as we proceed to the next slide. Let's look at the case where n is a multiple of 4 but not a power of 2. As we saw from the previous slide, in that case we can write our integer n as an odd number times a power of 2. So we'll write it here as 2p plus 1 times q. We're not so much interested in the structure of q here, although it turns out to be a power of 2. And there's 2 subcases to this, actually. If q is greater than p, we will write n as this sum here. And this sum equals this. You can see that by noticing that the minus 1 and the plus 1, the minus 2 and the plus 2, and the minus all the way up to the minus p and plus p, they all cancel. And then what's left is 1, 2, q plus p plus 1 q's here, and then another p appearances of q on this side from here to here. And so you get 2p plus 1 appearances of q. And as I noted, the other numbers cancel out. We can do an example. N equals 40. That's 5 times 8. Now our 5 we write as 2 times 2 plus 1. And so p is 2, q is 8. And then we plug that into here. So you have q minus p is 6. And we go all the way up to q minus 1, which is 7. Then we put in q, that's 8. And then we continue up to q plus p, which is 10. So we have 9 and 10, 2 more. So and you add these up and you get 40. Then the other case is when q is less than p. If we try to use this formula, you'll get a negative number here, which is okay if you want to use negative numbers in your consecutive integers, but you can make it so that they're only positive by using this form of the formula. This again adds up to 2qp plus q, which is the same as 2p plus 1 times q. And again, you have this cancellation of the 1s, the 2s, all the way up to q minus 1. And that'll leave you with 2qp appearances of p. And then the only thing that doesn't cancel is this q here, which you've added it here. And then you can factor q out of this and get 2p plus 1q. Okay, so kind of a quick explanation, but if you want to think through this or look at it in more detail, this does equal this here. So it's just another format, but it gives you all positive numbers in this case. So if we had n equals 52, we can write that as 13 times 4, and then that's 2 times 6 plus 1. So our p is 6, q is 4, and it fits this here. Q is less than or equal to p. And then you just plug into this. So you have p minus q minus 1. So p minus 3 is 3. And then you keep going until you hit p. So it'll be 3, 4, 5, 6. And then you have p plus 1 is 7. And you continue up to p plus q, which is 10. Okay, so you might want to try the next few just to get a feel for these formulas. Try doing 56, for example, or 60. In other words, the next couple of multiples of 4, and then see which one of these formulas fits. Okay, so that's a bit of a complicated problem. As I mentioned, there are a couple of links where you can get more information. The article from Halmos, or actually the book by Halmos, is pretty good. That's where I got most of this information. He explains it pretty thoroughly, and you may want to have a look there. On this slide, we have a puzzle that's a little bit similar to Sudoku, but quite a bit different also. We have a 6 by 6 square here, and the task is to populate this square with the numbers 1, 2, and 3 under several conditions. Each row is to have 3 3s, 2 2s, and 1 1, and each column is to have 3 3s, 2 2s, and a single 1. And there's additional constraints. These dark lines here, these, I'll call them separators. If you have a separator, then you need to, the requirement is that the same number has to be on both sides of the separator. So here we have it going horizontally, you have to have the same number. Then this separator here requires the same number above and below it. Here you would have another separator, so you'd need the same number above and below it, and all the way throughout wherever you have these bold lines. Then there's one additional constraint. 2 identical numbers in adjacent squares must be separated by a bold line. So in the one case, you have to have the same number on either side of this bold line, but if you don't have a bold line, then you're not allowed to have the same number. So you can't have a 2 here and a 2 here. That would be an illegal setup of the puzzle. So under those conditions, you want to fully populate this particular square. So I'm going to go through this example, and then I'll give you an example to work on as a problem. So let's look at this on the next slide. Oh, and one other comment. This comes from the book I've mentioned a few times, and there's even this particular puzzle with the lines as they are in here came from this book, and there's quite a few more examples in this book if you like this type of puzzle. Okay, so I'm going to solve the puzzle we presented on the previous slide in steps. So let's start here on the top row and look at this cell here. What can we put in here? Well, we can't put a 1 in here because we're only allowed to have one per row and one per column. In fact, you can't put a 1 anywhere near any of these bold lines because of that requirement. So 1 is out. What about putting a 2 in here? Well, if we put a 2 in here, then we have to put a 2 here, and then we have to put 3 3s in these 4 spaces. But we're not allowed to put the same number next to each other unless it's separated by a bold line. So we wouldn't be possible to put 3 3s in these 4 spaces without having 2 of them next to each other. So this kind of gives us a foothold. That means we have to put a 3 in here. And then that means we have to put a 3 here and a 3 here. How about this position down here? This is even easier because we're only allowed to put at most 2 2s, exactly 2 2s I should say, in a row. So if we put a 2 in here, we'd have to have a 2 here and a 2 here, so that's out. And of course 1 is also out. So the only choice for this is a 3, which means we have to put a 3 here and a 3 here. So we got a good start. Let's move to this middle diagram where I put in black where we started, and then the red ones are the additional ones that we're able to deduce. So if we have a 3 here, then we need to have a 3 above it, of course. And if we have a 3 here, we need to have a 3 above it because of this bold line. Because of this bold line, we need to have a 3 below it. So we can populate these as shown. Then here we can't have a 1 and we can't have a 3 because we already used up our 3 3s. So this needs to be a 2, which implies this is a 2 because of the bold line. And then that forces a 1 here. And then because we have a 2 here, we have to put a 2 here. So we're moving along pretty well. Let's look at the last column. So for these two squares, we can't put a 3 because we've already used 2 of them up, and we're supposed to have exactly 3 in a column. So, and 1 wouldn't work either because we're only allowed to have 1, 1. So this has to be a 2, both here and here. We can't put a 3 here because there's no bold line, and we're not allowed to put the same number next to each other unless we have a bold line between them. So this has to be a 1, and then this has to be a 3. So let's make everything that we have in this diagram here, we'll make that black, and then we'll just show in red what we're adding to this. So let's take a look here. What else can we deduce from what we've already done? So one thing is, let's look at this second from last column here. We have a 3 up here and a 3 up here. So we know we can only put one more 3 in here. And we can't put it next to this 3. And we can't put it on either side of this 3 because there's no bold line. So it has to go here. So now we have a 3 here, a 3 here, and a 3 here. And what about the 2? We can't put it here because there's a 2 here and there's no bold line. So this can't be a 2. So that only leaves this spot and this spot for the 2. And then we're forced to put the 1 here. So we have this row all settled. And let's look at this, this column. Columns are the up and down. Then this row here is, we already have this 3 now, and we know we need to have 3 3s, and we do have this bold line, so we're free to put a 3 here and here, and that settles this. Now, the only thing left is in terms of the additions I made here, is this 2. So why does this need to be a 2? Well, we can't put a 3 here because we're not allowed to have 2 things next to each other without a bold line. When I say 2 things, I mean 2 of the same number. We can't put a 1 here because we're only allowed to have 1 1 per row. So we're forced to put a 2 here. Okay, so we're pretty far along. The more you add, the more you've completed in the puzzle, of course, the easier it is to add additional ones. So let's kind of freeze this. We'll make everything black, and then we'll go to the next slide and we'll try to fill in the rest of these cells. Okay, so all the black numerals or numbers are what we had from before, and let's try to complete we'll add a few more. We'll complete it in this one here, but let's add a few more things. So let's look at this column here. We need to add another 3, so it has to either go here or here. And we can't put it here because there's no bold line, so we can't put a 3 next to another 3 unless we have a bold line. So we'll have to put that here, and that leaves only this place for the 1. We have a 3 here, and we could have added this 3 a long time ago, but kind of waited. Because of the bold line, we have to have a 3 on either side of this, so this has to be a 3. And then we have 2 more that we've added here in this particular diagram. So we have 2 3s. We need to add 1 more, but we can't put it here because we don't have a bold line. So this has to be a 2, and then that will leave this space here for the remaining 3. So let's make these 5 new items black and then go to the final solution for the puzzle here. Let's start at the top. So we can't put another 1 here. We could put a 2 or a 3. So maybe we need to hold off on this because there's some uncertainty as to what's allowed here. So we'll come back to this. Let's look at this column here. This row, I keep mixing row and column. This row here. So we can't put another 2. And we know we need another 3 somewhere. So it can't be a 2. It could be a 1 or a 3. But we have a 3 down here. So, and there's a bold line and we're forced to have a 3 next to a 3. So this needs to be a 3. And then that solves our problem up here. Since this is a 3, we can't put a 3 next to it. So this needs to be a 2, this needs to be a 3, and then this is the only place left, and we don't have a 1 yet, so this has to be a 1. So we've gotten that solved. Then this column has everything except a 1, and it seems like a 1 can legally be put in here. So we're good on that. We need one more 2 in this row. So that's fine to put that here, and then because of the bar and because we need another 2, we put another 2 in here, and then we've solved it. We've met all the conditions, and it's totally populated. So it took a bit, but you can see how you're able to reason logically. You don't really need to guess anywhere. You can reason logically to keep moving from one version or one level of this puzzle being solved to the next level. Okay, so this is from the same book that I mentioned. It's a different puzzle. You can see the bold lines are in different places from the puzzle we had before, but it's the same conditions. We need to populate this with 1, 3s, and 2s. You need to have the same number on either side of a bold line, either horizontally or vertically. And if you don't have a bold line, you have to have different numbers on either side, either horizontally or vertically. So I'll give you the solution later on, and you may want to pause here and give it a try. This is a tricky puzzle. I didn't get it. I needed to look at the answer from where I saw this. It's looks kind of simple on the surface, but there's a trick to it, which I didn't see. So we have Jill, we'll call Jill J, needs to transport a fox, which we'll call F, and a chicken C, and a box of lettuce L across the river in her boat. So it's kind of whimsical. However, the boat only has room for Jill and one other item. So it must be a very small boat. So either the fox, the chicken, or the box of lettuce. And so far it seems okay. Here's where the complexity comes in. So in her absence, the fox would eat the chicken, and the chicken would eat the cabbage. So how can Jill get all 3 passengers from one side of the river to the other without having the fox eating the chicken or the chicken eating the cabbage? I'll give you the answer at the end of this lesson, so you may want to play around with this a little bit. It takes quite a few steps actually to do this. That's why I gave these initials here, J, F, C, and L. You might want to draw sort of a diagram with the river and then showing who's on either side of the river and who's crossing and as part of the diagram. And you don't want to have to write out the whole names. You can just put the letters as abbreviations for what you're moving across the river and what you're leaving on either side. We have a couple of counter problems. What I mean by a counter is you have a meter of some sort and it's just continuously incrementing by 1. The first problem involves bits, so we only have 2 possible numbers, 0 or 1, to use on our counter, and it has 6 places. So we're starting from 6 zeros, and then we go to 0, 0, 0, 0, 0, 1, and then increment that 1 to that, and so forth until we get to 1, 1, 1, 1, 1, 1. If the counter runs through its entire range, how many such combinations will have at least one appearance of the bit 1? What is the total number of times the bit 1 will appear in all the different readings? So for example, 1, 1, 1, 0, 0, 0 counts as 3 appearances of 1. So you may want to pause here. I'll come back and give you the solution on this same slide. Okay, I'm back. Let's look at the solution. So the total number of readings is 2 to the 6th because you have 2 possibilities here, 2 possibilities for the second and the third and so forth. So for each of the 6 places we have 2 possibilities. So it's just 2 times 2 times 2, 6 times. That's 2 to the 6th. And only one of the readings is without the bit 1 anywhere, and that's the first one with all zeros. So the answer to the first question is 2 to the 6th minus 1. Regarding the second question, each of the bits, 0 and 1, appear the same number of times. So we just need to divide 2 into the total number of bits in all of the readings. So each reading has 6 bits in it, and we know there's 2 to the 6th total readings. So it's 6 times 2 to the 6th divided by 2, or 3 times 2 to the 6th appearances of the bit 1 as we range over all the values of our counter. And of course, since there's the same number of zeros, there would be 3 times 2 to the 6th appearances of zeros. We have another puzzle similar to the last one, but there's a couple of differences. One, we're going to talk about digits here, and the other difference is it has 7 places. So we have a counter again, and it starts from all zeros, but there's 7 of them. And then the values could be anything from 0 to 9 for each one of these. And then it runs until it hits 7 9s in a row. So if it runs through its entire range, how many such combinations will have at least one digit 1? What is the total number of times the digit 1 will appear? So the analysis is a little bit more subtle and slightly more complicated than the previous puzzle, but similar ideas. The answer to the first question is the difference between the total number of readings, which is 10 to the 7th, 10 possibilities for each of the 7 places in our 7-digit counter, and the those not containing the digit 1. So we need to take the difference between those two numbers, and the number of readings that don't have a digit 1 in it are gotten by filling the 7 positions with 0, 2, 3, up to 9. So we have 9 choices for each digit in that case. So that would be 9 to the 7th. And then we take the difference between 10 to the 7th and 9 to the 7th, and we get this number here, which is the total number of readings with at least one appearance of digit 1. For the second question, we again note that each of the 10 digits appear the same number of times. So the total number of times the digit 1 appears is 1/10 of the total number of all digits in all of the readings. So the total number of digits in all the readings is 7, because there's 7 digits, times 10 to the 7th. And then we divide that by 10. So the total number of appearances of 1 in all of the different readings is 7 times 10 to the 6th. There's an old puzzle, you've probably seen this, where you're asked to connect 9 dots that are in a square array without lifting your pen off the paper and only using 4 line segments. So I've shown the solution here. So you have these 9 dots, and you get 4 lines that go through them. And the hard part is that if you've seen this for the first time, is that you need to go outside of the square formed by the 9 dots. And so you start here and you go up here, then you go down. Then the tricky part is you go outside of the square and then you go across. So it only takes 4 line segments to cover the 9 dots. And the same is possible if you have an n by n array, and you can use only 2 to the 2n minus 2 line segments. So in our case here, n is 3, and this is 6 minus 2 or 4. So this is what we've done here. So the problem I pose to you is try this for n equals 4. In other words, we have 4 by 4 dots, and then n equals 5 and n equals 6. And I'll show you. The solution starts to repeat. So I'll show you the answers, but you may want to try it first. For n equals 4, 2 times n minus 2 is 8 minus 2 is 6. So we're allowed 6 lines now. And you see here we have 4 by 4 array of dots. And we kind of start with the same idea from the previous solution, although we have to add to it to get our answer here. So we start here, cover 3 dots, then we go down, we go outside of the square, then we go this way, and then what's new is we continue to this last column, then we go down, and we go over. So 6 lines are able to cover the 6 line segments, I should say, are able to cover all of the 16 dots. Okay, so let's look at it. In the next slide, we'll do it for 5 and 6, for n equals 5 and 6. But you may want to try it before I show you the answer, because you kind of have an idea of where this is going, just the way we've extended it here. So let's look at the case for n equals 5. We're allowed 8 line segments. So again, we start as we did before. We start here, we go up diagonally, then down, then over this way, then this way, and then down. So up to here, it looks like the 4 by 4 solution. Then we just continue to this row on the left. Then we go up, so we get 5 more that way, and then we go across and we get the other 5. So you can see that's just an extension of the case for n equals 4. And I also put n equals 6 here. So if we made this 6 by 6, you can see what you need to do. You need to just go down and then over, and that'll give you the case for n equals 6. And hopefully you can see what the next one is, which I put here. N equals 7. You would just continue and then go here. So the hard part was actually n equals 3. We have the 3 by 3. Once you have that, you're just kind of adding around the edges. And so we've kind of given I guess a high-level proof of the general case when we just have n by n. It's just an extension. You just keep adding and getting bigger and bigger, going around your extended square. The counterfeit coin problem. We're given 8 coins that appear the same, but one of which is counterfeit and is lighter than the other 7. So that's the information we're given. You might want to think of pennies or something like that. So 7 of them have the same exact weight, and then the 8th one looks like the other 7, so you can't tell just by looking at it, but we're told it's a little bit lighter. What is the minimum number of weighings that needed to identify the counterfeit coin using a balance scale? So you can put your coins or any combination. You don't have to use all 8. You could use 2 of them, at a time, or whatever you'd like, out of the 8, and you put them on either side of this balance. And if the light coin is here, and say a normal coin is here, then this would go down and that would go up. So what's the minimum number of weighings you need to do to decipher the problem and find out what's the light coin out of the 8? So this is a bit tricky. It takes some doing to figure it out. The solution is that we create groups of sizes 3, 3, and 2. Now we don't know where the light coin is at this point, but we've just divided the coins into these 3 groups. We put the groups of size 3 on opposite sides of the scale. If the groups of 3 balance, then of course they're all of the normal weight, and that would mean the fake coin is in the group of size 2. And then our task is pretty easy, right? We just put the one of each of the 2 remaining coins on the either side of the scale, and then the side that goes down is the normal coin, and the side that goes up is the lighter coin, and so we're done. But this may not happen. We may not get lucky and have the groups of 3 balance. So if the groups of 3 do not balance, the lighter fake is among the 3 coins that go up. So we've isolated now the lighter coin to the group of 3. Take any 2 from the group that contains the lighter coin, in other words, from the group of 3, and put them on the opposite sides of the scale. If they weigh the same, then we know it's the other coin, that's the lighter one. And if they don't balance, then whichever one goes up is the lighter coin. So either way, it only takes 2 weighings. The second approach here, the second case, is a little bit more complicated than the first, but either way, you only need to do 2 weighings. So it's a little bit surprising, given that you have 8 coins, that you can cleverly find out which one is lighter out of the 8 by just doing 2 weighings of the coins on the scale. So let's look at our problem that I gave you earlier, the tower square problem. So I'll give you a hint first, just to get you started, and then you may want to pause here before I give you the full solution. The hint is this row here. We know that we have to put 3 3s in a row, I should say, and we know that if you put a 3 here, we're forced to put a 3 on the other side of the bar and on the other side of the bar here. And we also know that we can only put 2 2s and only 1 1. So we're forced to put a 3 here, which means we have a 3 here and a 3 here and a 3 above it and a 3 below it here. And we can't put a 1 here because then we would have to have 2 1s, and we only can have 1. So this has to be a 2 and this has to be a 2. And that leaves 1 for this one here. Okay, so that gives you a start, and I'll give you the rest of the solution, but you may want to try completing it without looking at the answer, which I'll give you on the next slide. Let's continue with the solution here. On the left and in black, I copied where we stopped from the previous slide. We can add a few more, which I'll explain. So we can't put a 1 here because of we're only allowed to have 1 in a given column or a row, for that matter, and we already have a 2, so if we put a 2 here, we would have 3 2s, and that's not allowed. So this needs to be a 3, and then both of these need to be a 3 because of the bar. And then the question is, what can we put here? Well, we can't put a 2 here or here because there's no solid line, and we're not allowed to put the same number next to each other if we don't have a solid line. So the only other choice is to put the second 2 up here. And if we put a 2 here, then we have to have a 2 here. And we can't put a 1 here because of the bar. We're only allowed 1 in a row. So this would have to be a 3. We have a 3 here, we have a 3 here. We can't put another 3 here because we're not allowed to have 2 3s in a row without a bar, which we don't have here. So that means this has to be a 1. Then the remaining 3 for this row goes here. Then because of this bar and this bar, we have a 3 here and we have a 3 here. So let's move on to the next step, so to speak. So we'll make everything in here black, and then I'll just explain the additional things in red in this middle diagram. So we have a 3 here, and we could have done this over here, but I didn't want to crush everything together. So we have a 3 here implies that there has to be a 3 here, and then on the other side of the bar we need to have another 3 here and another 3 here. So that gives us 3 more positions in here. Then we can't put a 3 here. Sorry, we can't pointing here. We can't put a 3 here because there's no bar. So we'll have to put the 1 here, which means the other 3 goes down here. Now we have a few more that we can figure out on this row here. We can't put a 1 here because we're only allowed to have 1 1. So this has to be a 2. So that gives us a 2 here, a 2 here, and a 2 up here. And then the only spot left for the 1 in this row is here. So we put a 1 here, and then we have the same issue here. There's only 1 spot left for the 1. So we'll have to put that down here. So we're almost done. Let's go to the final diagram here on the right. And again, everything that we've already done, I put in black, and then we'll just add a few more, which gets even easier because there's only a few spots left to work with. So we have a 3. Let's work on the bottom here. We have a 3 here, and so we have to put a 3 on the other side of the bar. And then we have we have to put 2 2s, so it doesn't matter. These 2 spots here have to be 2s. So we have a 2 here and we have a 2 here. So now we've completed the bottom half of the grid. There's only 1 open spot here, so that needs to be a 2. Completed that. There's only 1 open spot left here now that we've completed this, so that has to be a 1. So now we're just down to this little bit left in here. We need to have another 2 and another 3 here. We can't put the 3 here because you'd have 3 next to each other. So that means the 3 has to go here, and the only choice left is to put a 2 here. And that seems to be legal. It's not violating any rules. Then this is almost done except for the 2. So we'll put a 2 here, and this is almost complete except for the 1. We'll put a 1 here, and we're done. So that's the solution. And as I mentioned at the beginning of this, the book I took this from, which I gave the reference to, has quite a few puzzles of this form. So if you like these type of puzzles, you might want to get a copy of that book. On this slide, I have the solution to the river crossing problem from earlier. So we start with Jill, the fox, the chicken, and the head of lettuce on one side of the river. And then the river is here, and then this is the other side of the river. So the only choice to get started is to move the chicken. If we move either the fox or the lettuce, then we'll have either the fox eating the chicken or the chicken eating the lettuce. So we have to move the chicken first. That's maybe an easy step. Then Jill comes back, and you have the fox and the lettuce that remain. And the fox doesn't eat lettuce, so we're okay here. The tricky part comes next. Jill takes the fox across, leaving the lettuce here. She gets across, and she knows the fox will eat the chicken, so she has to take the chicken back. That's the part that's a little bit counterintuitive because it it looks like you're not gaining anything here. So she brings the chicken back. Now here's the key. She brings the lettuce to the other side. The fox won't eat the lettuce. So we're good. And then Jill goes back one last time, gets the chicken, brings the chicken across, and now everybody is on the other side. So that was the last thing for this lesson. I'm planning a couple more lessons. Once I record them, I'll put them up on the my YouTube page. And if you have any suggestions, let me know, and I'll think about maybe doing even more lessons. Okay, so thanks for listening, and stay tuned.